Hello again. This is the third part of this presentation on type erasure and how to understand it via the implementation of std_any from scratch. In last episode we developed a toy implementation of std_any from scratch and we've demonstrated that it works at least according to those tests that I've written here, or better, this little main program that tries to exercise all the API that we've provided for it. We also run into a last minute change because I had initially implemented anycast as something that just goes undefined behavior if the caller passes a type that is not the type of the object stored inside of std_any, and that's not what the standard prescribes for std_any. What it prescribes instead is that it should throw, and eventually I had to also implement this member variable here type and initialize it appropriately and then use it in anycast to actually detect that the caller is requesting the wrong type and throw an exception accordingly. Anyway, yeah. So we have a minimal implementation of std_any, and now the question is how close this implementation is to the actual implementation, at least one of the actual implementations, for instance the one you find in GCC. Let's look at it, and we have above the implementation we've come up with, and the one below is the actual implementation from GCC. Yeah, so what are the similarities, what are the differences? Actually, as soon as I search for the class any, not many lines below I can already see the first similarity, that there is a void pointer, just like we've used the void pointer here. Where is it? There. But it's used differently, and another thing you can notice is that whereas our void pointer is a member of the class any, this void pointer here is not a member of the class any, it's a member of the union that is a member type of the class any. So there is one more indirection layer, and the reason for that is that whereas for us the void pointer is the only way we can manage the object that is passed by the caller, or a copy of it, in the case of GCC, this void pointer is just one of two possible ways to store the object. And again, one is exactly what the same way we've used, which means storing the object on the heap and having the void pointer point to it. The other way is to have the object in a static buffer. By static buffer, I mean this mbuffer thing here. This is just an unsigned char, where char does not have anything to do with text, with strings or character type. Char is just a byte. So this mbuffer here is simply an array of bytes, so it is essentially an area of memory of this length. And what this is just the size of the thing above, so it's the size of a pointer. That means that on a given architecture, this is just a number. And that's the whole size of this M buffer. So this is a very small buffer in which we can store the object that has to be stored in the any as long as it is small enough. Otherwise, we can't store it in here and we have to rely on the heap, and so essentially do what we've done in our toy implementation. And whether the one or the other storing method is used depends on the size. It's not, you cannot see it here, I will show it later. It depends on how large the actual object that we are storing in any is. How can we see where this... Hello. Where can we see this conditional? Well, we just look for where this storage class, this storage union is used, and we find it's used here. So we have this internal member alias for an integral constant of type bool with the value known at compile time, this one. Well, this is maybe not extremely familiar to young C++ developers, but think of it as a compile time boolean where the value of the boolean is this one, and again it is known at compile time, and it is simply the conjunction of two booleans. One is defined here, and it is essentially true if the type TP that we are passing, TP is this one, so it's the template argument that you can pass to this template alias. If that TP is no through move constructible, which means if it is move constructible, if when move constructed it promises not to throw, then safe will contain the value true, otherwise false. And then fits is another boolean, again compile time, which is true if both this and this are true, regardless of the alignment. I don't actually know exactly what that is. the size is the important thing, which says if the size of the type is less than or equal to the size of storage, then this is true. So this internal thing here is a compile time boolean, and you find out the value of that boolean by passing a type as a template argument, and that compile time boolean will be true if that type is no through move constructible and if it is small enough. And where is this internal thing used? Well, you can see it's used here. It's used to define the manager. Again, this is a template alias, so you have the manager given a type. And this manager is conditionally the internal manager or the external manager, depending on whether that value of the compile time boolean I just described is true or false. And again, that compile time boolean was true if the type is no through constructible and small enough. So if it is small enough and no through constructible, we use the internal manager. Otherwise, we use the external manager. What are these managers? We can jump to the internal manager. And so let's look, for instance, at the class sManage. This sManage function, you see it has the same signature for manager internal and for manager external. And the signature is that it takes an op. What is an op? It's essentially a tag for an operation, and we will look at that in a moment. It takes a pointer to the any on which you want to perform the chosen operation, and then it takes a pointer to some additional argument for the operation to be performed. Let's look for a moment at what op is. Op, it's just an enum, so it is essentially one of 5 possible values. And so essentially this sManage function takes one of those 5 values to select the operation that the caller wants to do, and then it takes the any on which via a pointer on which the operation needs to be performed, and then possibly additional arguments. And that's the true for the internal and the external manager. Now the question is, how is this implemented? Well, we can just jump to the implementations. Down here there is the implementation for manager internal, and then later there is the implementation for manager external. Let's look at the external one, because external is the one that should look a bit like the one we've done. And what does this manager do? Again, it takes the op pointer, and that op pointer is used to, that op operation tag is used to switch, as you can see here, between the various operations that you might want to do on the any. Before going to the switch, this _m_ptr is the void pointer that corresponds to our void pointer. And as you can see, it's not directly inside the any, but there's a bit more levels of indirection. mStorage is the storage, the union that can be either the void pointer or the buffer. But ultimately, this is mirroring our void pointer. And this is being static casted to the pointer to the type that is inside of the any. Because look, that the manager is aware of the type, and so it can do the static cast on the void pointer. And that's exactly what we are doing on this line here. We're actually doing it more than once. We're doing it here, we're doing it here, and we are also doing it, I think, in the any cast here. So we have kind of sprinkled this idea of casting the void pointer to the correct type in multiple places, whereas this is being done in a unified place just here. This is where the pointer is being casted to the correct type, and so this makes it available for the various operations. And if we go look at the operation for destroy, for when the destroy tag is passed, that's just delete on that pointer, and that is mirroring the destructor here. It's doing this. Indeed, our delete function here is calling just delete on the pointer being cast to the right type, whereas this is already cast and then delete is being called. Another thing, we can look at clone. It's here. The clone function for us is something that does new on the given type, again passing the pointer cast to the correct type, and again this is the pointer cast to the correct type, and this is doing new on that very type. But this is what gets done when you require that an object of type any is actually cloned. So this is where the cloning happens. That's the creation of the new object that is stored inside of the void pointer of the any in which the cloning is happening. But then it also copies over the manager. The first line is mirroring a call to the function clone that we've initialized here, and this one is mirroring these other 3 lines, because the manager is dealing with all the operations, with deletion, with cloning, with extracting the type, and so on. So by copying the manager, you're copying the whole struct that takes care of all of these things together, which is this very struct we are looking at. Op get info, which is doing exactly the same thing here, is calling type ID operator on the type and then getting the address. That's what we were doing here. So these are all the various similarities. One thing we can see though is that smanage for the internal manager is a bit different. Things are done differently because this is for when you've stored the object not on the heap but inside any object itself in that static buffer. And that means that, for instance, the operation to get the type is exactly the same because you just have to call type ID on the type of the object, so that doesn't depend on how you've stored the object. But clone is different. It is still doing the member-wise copy of the manager because when you clone any object, you want to be able to destroy it, to copy it further, and so on. So you need to copy the manager. But the actual cloning of the object is not done via the new expression, but via the placement new operator. This is not the same new we've used and that the manager external uses. This is the one used by manager internal. It has the : in front of it. And before taking the type that needs to be created and the value from which you want to copy it, it takes as a first argument the address of where you want to put it. So this is actually not an address on the heap, but an address on the stack, because it's just the address of that unsigned char that has a fixed size. That on my machine, as you can see, it's 8. So this is a bit different, and the destruction as well is also different. As you can see, it doesn't call delete, but it calls explicitly the destructor of the type that is stored in the any. So yeah, we've seen differences and similarities between the GNU C++ implementation and our toy implementation. That kind of reassures us that we've made a sensible design, or at least half a design, because we're not branching on the size of the stored type to avoid using the heap and allocating on the stack, which is more efficient. And so that is something you want to do in order for any to be mostly efficient when you are storing into it, say, an int, a double. In our implementation, we are allocating on the heap even just for an int or for a double, and that's bad, but it's an orthogonal decision to the decision of using type erasure. Another thing I wanted to show is the similarity with the prototype design pattern. So I've opened up this Wikipedia page on the prototype pattern, and I will scroll down. There is C++ 23 implementation. As you can see, we have here the base class of a hierarchy, and then we have some derived classes, for instance room. And the question is, if I'm given a pointer to a base class that points to an object of a derived class, how can I make a copy of that? If you try out without doing anything like this, you're not gonna get a copy. So this is the solution to that the base class should have a clone method that returns a pointer, in this case a unique pointer, to the base class, and then it's up to the derived classes to implement that clone method by doing a copy that is aware of the type they are. And they still return via a unique pointer to the base class, but they are creating an object of their own class, which is a derived class. And clearly, start this is the actual object, so dynamically it has type room because we are in the class room, and so we make a copy of that and we store it in a unique pointer, but then we return it as a unique pointer to the base class. And this unique pointer is playing the role of our void pointer, because our clone method returns a void pointer, and that is corresponding to the pointer to the base class, which is less specific than the derived class. Like this void star is less specific than a pointer to anything else. And then this one accepts the void pointer to the object that we want to create, and this is corresponding to this pointer, with the difference that we have to start from the void pointer to one payload, retrieve the original type, make a copy, and then return it via the void pointer. But in this case, the first part of what I just said is actually happening in an automatic way, because we are writing, like, the clone method is being implemented in a derived class, so that this pointer is pointing to the actual object, and when we dereference that, we get the object of the actual type. Like the pointer this is not a void pointer, is a pointer of the correct type. So that's a slight difference. I hope that this similarity between the two things is conveyed. Is a bit like the prototype pattern is a simpler problem than type erasure, but it shares similarities with it. So that was it about that point. And another point I want to mention, the last one here, is just an observation about the code we've written, which is, as you can see, beside the constructor that accepts any possible, like all possible types, and that is a templated constructor. So in order to make it work for any type T, you have to keep it in a header, which is the same place where you define the class. The other member functions, like the various constructors and the copy assignment and the move assignment operator and the destructor as well, they are all non-templated. That means that in theory, that's not what is done, but in theory they could be just declared here in the header and then defined in a CPP, and you could compile that and then you would link it against clients. That's just an observation. As you can see, that's not what is done in reality, because it will probably reduce the efficiency of this abstraction. But one thing that kinda is related to it is that std any, like std function, it cannot store move only types like a unique pointer because it is not copyable. Why is that the case? The reason why one could ask this question is because there are many things in the standard library that are like, or in C++ in general, where you say, oh, if this thing is copyable, then that thing is copyable. For instance, if you have a vector of shared pointers, the shared pointers are copyable, and so the vector of shared pointers is copyable. And if you have a vector of unique pointers, your unique pointers are not copyable, and so the vector of unique pointers is not copyable. So there is this kind of transitivity, and so one could wonder, why can't std any accept types that are non-copyable? You could think, oh, if the type I'm passing is copyable, then std_any is copyable, and if the type is not copyable, then std_any is not copyable. But that's not possible, because std_any is a single class. When you have a vector of shared pointers, of a vector of unique pointers, those are different types. One is vector angle brackets, shared pointer angle brackets, whatever, and the other is vector angle brackets, unique pointer angle brackets. So they are different types. So they spring from a template class, which is vector or list or whatever. When you instantiate with one type and with another, then the various member functions will be instantiated or not instantiated depending on some conditional, like if that is copyable, then define the copy constructor. If it is not copyable, then don't define the copy constructor. Any cannot do that because the copy constructor is statically defined here. It doesn't depend on a template parameter. You don't have a type on which you can branch. Yes, we captured the type during the construction in these lambdas, and so these lambdas do the right job, but that's a runtime information. The copy constructor doesn't know at compile time if it is dealing with a copyable type, because there is one constructor and it will be always the same irrespective of what type you store in the any. And the same holds for the move constructor, copy assignment, move assignment, destructor. They are not templated, so there is one only version of them, and it must work for everything. Then that means that any in its entirety cannot work with move only types. And so one could ask, what if I want? Well, that means you could write your own version called any_movable or move only, and then you would define that for movable types, and that means you wouldn't write a copy constructor, or you would delete it, and then you would implement a constructor in such a way that it rejects types that are copyable and would only accept types that are move only. So yeah, that was it. This is the end of my presentation, and I hope you enjoyed it. I hope you understood what C++ type erasure is to its tiny details, and I guess the challenge is to try implementing std_any from scratch again without looking at these or other presentations, and see what you can come up with, and maybe try to implement std function, which is a much harder beast to implement. Thank you very much for joining me, and let me know in the comments if you want to hear me talk about some other topic. I'm excited about explaining more things, not just about C++, but programming in general. I like programming languages in general. I like C++, and that's what I've been working on for 6 years. But in my spare time, I've programmed also in Haskell, doing some personal projects. I can do a little bit of JavaScript, and I'm eager to learn more and more. So please let me know if you want me to talk about something. Bye.